today I want to show you the power and simplicity of SQL and why and how you could maybe leverage it for your use cases. So I will give you some introduction of Flink SQL first, then I will give you a short introduction into the SQL client, and then I will demo Flink SQL in action using the SQL client CLI. So first of all, who is Data Artisans? I think you already know that. We are the original creators of Apache Flink and providers of the DA platform and streaming ledger. So first of all, who is actually using Flink SQL? Because Flink SQL is around for a couple of time, and actually we have a very big user base already. So one of the biggest Flink SQL users is Alibaba. They are also still contributing. Huawei is also using it. Both Alibaba and Huawei are using Flink SQL in their cloud offering. Then Lyft, Uber, and Yelp, they also have their internal platforms that they provide to their data science teams and so on. So first of all, what is there in Flink right now? So as you may already know, there is the data stream API. This is our main API in Flink. You can do batch and stream processing with the data stream API. There are some tooling already prepared for you, like you can use tumbling session or other windows. If you want to do more low-level stuff, then you can also go one level deeper. We provide the process function for stateful event-driven applications where you have direct access to timer service and state, like all the primitives you need for stream processing. But actually, there is also a new API on top of the data stream API, which I'm going to talk about now. So we have two relational APIs, a SQL and a table API. Compared to the data stream API, this builds like the concept of a dynamic table around around an API, so that you can imagine a stream as a table, basically. So how do the relational APIs look like? So first, on the left side, as you can see, it is SQL, it is ANSI SQL, so no Flink-specific language. No, we are using pure SQL. And if you want to have like a more programming style approach, maybe embedded into your entire data stream program, you can also use the table API. There you can, of course, see which operations are available. You can click on the function, you get Java docs if you need that. So both APIs might be quite useful. And the very important thing is both APIs are compiling down to the same program, as you will see soon. They are unified APIs for batch and stream processing data. And the very important thing is every query specifies exactly the same result. It doesn't matter if the input is static batch data or streaming data. The result is always exact, accurate, and the same. So how does the query translation works underneath? So this is the rough architecture of Apache Flink's table and SQL API. So as you can see on the left and the right corner, we have the two APIs. Both APIs have their own validation phase. In the core, you can see we are using the Apache Calcite framework. So for the SQL part, we are using Apache Calcite's parser and validator. We are using Calcite's catalog, and we are connecting two external tables. You can also convert a data stream or a data set into a table. Everything is then translated into a logical plan. This logical plan is then optimized depending on the environment, either using data set rules or data stream rules. And then after the optimization, everything is translated into either dataset or data stream plan, and then finally into the API calls underneath. And as you might have guessed, dataset is for bounded batch data, and with the data stream API, you can do unbounded, but also bounded computations. So let me quickly explain how we actually achieve the same results for batch and stream data. So let's pretend we have a file, and this file contains some clicks, and we want to perform some SQL query on top of this file. So in this case, we are just counting the URLs, and we group by the user ID. So how would a batch processor usually do that? Actually, it's not very transparent to us. So usually the batch processor would just read the entire file. It would compute something, and at the end, it would just dump the results into maybe a file or something. Right? So the input data is read once, and then the result is also produced once. So how would it look like in a stream if this clicks file is actually a stream? So the interesting thing is the result is not there immediately. It enters Flink row by row, basically. And what Flink is doing, or Flink SQL API is doing underneath, is it maintains counters and other state that is necessary to maintain this running or this standing query. And it also sends updates in case a counter is increased. So in this case, Mary has just a count of 1, then Bob comes in, still a count of 1. But once Mary is there for a second time, we have to update the count that we previously emitted. So the input data is read continuously, and then the result is also updated continuously. But as you can see, both results, batch and stream results, are the same in the end if you materialize the stream. So why is actually this batch and stream unification so important? So there are two important aspects. First is the usability, because we don't want to have a custom SQL syntax. No, we want to have SQL that is portable. I mean, the SQL language is out there for 40 years. It won't change in the future, I think. So you can reuse your SQL statements also across platforms if you want to. We want to have SQL semantics, so no stream-specific results, which means you can also use the tools that are out there that producing or generating some SQL for input into Flink SQL. And portability is a very important thing if you look how we process data in the past. So on this timeline, you can see how usually data is processed or was processed. Usually you have some query, and then you perform this query on chunks of your actually never-ending data that is coming in, right? In either a daily or nightly or monthly batch job. The nice thing about Stream SQL is you can decide where you want to start your job. You can start your job maybe at the start of the stream or somewhere in the middle. You can compute something with data from the past, but you can also get insights into the data that is happening, or the computation that is happening now. And as it is continuous, you can also let the query run forever, and you can also compute the future with just one query. So the question is actually, how do we achieve the same semantics in SQL? And actually, this is not a very new technique. So maybe you have heard of materialized view in databases. Materialized view also are defined by a query. And for efficiency, usually the database maintains a materialized result of this query. So what happens usually underneath is that the query usually it has no access to the base tables, and it does not need access to the base tables. It consumes the logs for the underlying tables from the database and updates its internal state. So this materialized view maintenance is very similar to SQL on streams, and as in materialized view maintenance, there are also like updates, insert, and deletes that happen internally. So how do continuous queries in Flink look like? So as I said, the core concept behind it is a dynamic table. So you don't have to think about a materialized table that is persisted into state. This is not the case. So dynamic tables are just a table that is defined by a query. And Flink tries to maintain this query and just stores in state what is needed to produce a stream of change logs as the output. So as you can see in this example, if we would have a stream, we would logically convert this stream into a dynamic table. Internally, there is then a continuous query running that does some state computation. You can derive another dynamic table out of a dynamic table, or you can also convert this dynamic table back into a stream. So you can go back and forth at any time. If you look how the stream and dynamic table conversions happens, there are actually 3 different types of how you can convert streams and tables. So for example, in the upper right query, we have a very simple select from where statement. This statement is just an ETL statement, so we don't produce any deletions. So we are actually always consuming a row, we are transforming this row, and then we're inserting it to the downstream operator. So we are calling this the append conversion. If you think about it like a table, then you would only append rows to this table, basically. The right bottom query is a little bit more complicated because, as in our motivating example, you have to update the count whenever there is a user coming in. If you have seen this user before, then you have to update the count. If it is a new user, you just have to send an insert statement. So there are basically 2 types of conversions that you can do with this dynamic table and stream conversion. So either you perform an abstract conversion, meaning that you have a key, it can also be a composite key, that is defined. In this query, for example, you could use the user ID because this is a unique key that the query defines. You can use this key, for example, to continuously update Elasticsearch index, for example. So what is basically needed in the stream is just an upsert, which means there is an insertion or an update, depending if the key was present before, or a delete if you want to delete this key. We also support retract conversions. Retract conversion means there is no key defined. So whenever we update a count, for example, we first have to send a delete message with the old count, and then we insert a row with a new count. So you always have these 3 possibilities to convert a stream and table. So let me quickly talk a little bit about SQL features that we are able to do right now. So as you can see, Flink already has a large set of features. So as you have seen, we already support very simple things like select from where queries. You can use group by in SQL statements. Group by can be used both in a regular standard SQL way, like a non-windowed, but this might have effects on your state size. If you want to do a little bit more, want to do processing in a little bit more streaming fashion, we offer tumble, hop, and session windows. These tumble, hop, and session windows are also implemented in Apache Calcite, and I think they are also implemented in Apache Beam, so they are also kind of an industry standard already. We also offer different kinds of joins. Also in a windowed and non-windowed fashion, depending on your use case. For a windowed join, the nice thing is that you can also bound the memory state size. The non-windowed join might consume more memory underneath, but both joins are implemented in inner, left, right, full outer joins, so all the regular join semantics that you need. All these operators are implemented both in batch and streaming, so you can also execute windows on the dataset API if you want to do it. There are also operators that might make more sense just for streaming, but I'm pretty sure they will also be implemented in batch at some point. So here we have over windows. So I don't know if you are familiar with the over windows. These are the windows that the SQL standard defines, where you can look at the surroundings of a row whenever a new row is inserted. We have different unbounded, bounded preceding semantics for that. And for the batch side, we also support things like union, intersect, accept, and order by. Especially if you want to do things like ETL pipelines, it might be quite useful to see what data types SQL already supports. So we have full support, basically full support for all data types that are also supported by Flink itself. So we have POJOs, and we also recognize those POJOs, so you can have access to nested fields if you need them. We support maps, arrays, and other nested types. And we also have a large set of built-in functions, so over 150 functions, like hash functions and time functions and so on. And if there is a function missing, you can always implement your custom UDFs. We have different types of UDFs where you can extend SQL, like scalar functions, table functions, aggregate functions. I would just look into the documentation if you need more information about the available functions and how you can extend Flink SQL. And there are also upcoming features. My colleague already talked about that during the keynote. We are working on stream enrichment joins, which means we have one table that is periodically updated, and you maybe just want to match that with a table that is just appended. So you want to basically enrich the stream that is streamed by this periodically updating table. We also support, maybe support complex event processing soon with a match recognize clause. And we are also working on improving this whole ecosystem around SQL, like having a more tighter integration with connectors, formats, and catalogs. So if you're interested, I would suggest to just check the Jira issues that are listed here. So what can we actually build with all these SQL features? So as I said, data pipelines basically, which is a very reoccurring task at companies. So you can transform, aggregate, and move events in real time. You can have things like low latency ETL, which means through the streaming nature, you can convert the stream both into a file, into Kafka, into a database. So you decide how you want to do that. We can perform more complex tasks like stream and batch analytics, both on bounded or unbounded data. The change logs can be materialized, for example, in Flink's queryable state, or in Elasticsearch, for example, or some other key value store. And then you can just connect it with some dashboards, for example. So use Flink SQL as the processor for building up your materialized view, and then just build a dashboard against the key value store, and then you're basically done with your use case. So before I start with the demo part now, I quickly want to show you the newest feature of this whole Flink SQL ecosystem, which is the SQL client. You already have seen some demo in the keynote this morning, but I will also show you some demo now. The Flink SQL client is the newest member of this of the SQL family since Flink 1.5, and it allows you to not only play around with Flink SQL, but also see the results as they come in from the cluster, and you can also submit long-running detached queries. So the general goal of the Flink SQL client is basically you don't have to write a single code of Java or Scala anymore, just plain old SQL and a YAML file that defines some of the parameters like a parallelism or some other deployment properties. We provide drag and drop SQL jar files, which means you don't have to care about Maven and shading and dependency issues anymore. Just drag and drop the SQL jar files into the library folder, and then you can use this connector or format. Everything is built on top of the SQL API, which means whenever you need a function, just look into the Flink SQL docs, and then you know if this function is supported or not. So here's just a very rough configuration file, just to visualize a little bit how such a YAML file can look like. So it's a little bit small, but you can see we're defining some table source here. In this case, this table source is executed in append mode. We define a connector, which is in this case just a file system connector. We define the format and some types of the format and some parameters that depend on the format, like a line delimiter or a comment prefix. Yeah, and then we're basically done, and we can use this connector in the SQL client. We can also define things like views, or also UDF functions are defined here, and as I said, also like things like execution properties. If you need more information, just visit the SQL client documentation page for this. So I quickly want to explain how the SQL client works underneath. So as you can see, the SQL client is in the middle, and it's actually split up in two components. The left component is the CLI, and the right component is the gateway. So the gateway is, as the name suggests, is the gateway to Flink, basically. So it performs the optimization, it talks to the Flink cluster, and it can also retrieve the results back so that you can play around with Flink SQL, and the gateway will then give the results to the CLI and will print it out to the user. Both gateway and CLI can be configured with YAML, which means you can have a global YAML configuration, and then you can, depending on your current SQL session, you can also have session-based configurations with data sources that you just need in this session, for example. If you want to get more serious and you want to really submit something long-running to Flink, you can submit detached queries with a so-called insert into statement. This means the gateway will just submit this job to Flink. You get information where this job has been submitted, like the cluster ID and the job ID. And from now on, you can shut down the SQL client. The query will run in Flink, and you can monitor it via the web interface. So now it is some time for some action. The nice thing is everything that I will show in this session is basically online. So if you are interested in this whole thing, just visit github.com/dataartisan/SQL training. We are using a Docker image there, so you can just download this Docker image, and you will spawn up a little Flink cluster with Kafka inside, an Elasticsearch sink inside, and pre-configured sources and sinks, so you can start with your first SQL queries. And this is what I'm doing right now. So I'm starting the SQL client. There is a thread in the background running that inserts some rows into Kafka so that we have a little bit more like a streaming fashion program. So first of all, let's just type something very simple. The simplest thing that you can do is, why not a hello world? Maybe it is a little bit too over-provisioned because we are running a Flink cluster in the background just for a hello world program. But we can see the Flink job here. Yeah, it's completed already. Yeah. As you can see, a very simple streaming job. Okay, let's do something more complicated, but without any data sources. So this is also just for demoing purposes. Here we have a SQL query where we just generate some names with the values clause, and then we're just counting this name, and it's a word count basically. Yeah, and as you can see, Flink also computed this word count. The interesting thing here is what you can see here is the so-called table mode. So we are materializing the stream of change logs already in memory for you so that you can immediately see the resulting count, right? So you can also select something here, you can open the row, you can also go back and leave this mode. If you want to see more about the internals, you can also change the result mode into the changelog result mode. And then you can see how the changelog stream is actually inserted or comes out of Flink. So in this case, you can see there are a lot of insertions indicated by the plus. And since Bob is there 2 times, we have to first retract Bob, the old count, and then we insert the new count here. So let's go back to the old mode because it's more useful, I think. So let's do something more complicated. So as I said, we have something prepared already, so let's look into it. We have some tables here. Maybe we want to explore these tables a little bit. So So here we are reading from Kafka, and as you can see, the results are streamed in. So maybe we want to first explore our data a little bit. So we are performing some investigation or data exploration. Like maybe we want to know, in this case, by the way, I haven't explained the data set. So we are using the taxi ride example. I think it's a very prominent example in Flink, which is a event stream of taxi data, so you always get a result. Always get a start event and an end event for every taxi ride in New York City. And this you can also print this the schema real quick. Just a second. Taxi rides. So this is the schema of this data source. You see a ride ID, taxi ID. A Boolean flag that indicates if it's a start or end event, and some coordinates, and the road time when this event happened, and the passenger count. So so let's do some data exploration. In a batch job, this query would run a long time because we have a lot of data. The nice thing is with streaming, we get immediately insights what is going on in our job. As you can see, the average passenger is a little bit boring because apparently the average passenger is always 1. And on the right side, you can see how many rows we already computed that went into this average passenger count. Okay, so let's do something more complicated. What about some streaming windows, for example? So here's an example of how you would define a tumble window in SQL. So what we are doing here, we're grouping so we are mapping the coordinates to some area ID, and then we are grouping on the area ID, if it is start or end event, and we are grouping on a tumbling window of 5 minutes. And then we just perform a count per window, and we're only considering taxi rides that happened in New York City. And since we are not interested in small counts, we just filter out counts that are smaller than 5. As you can see, this query works, and you can also see it running here. Okay, another example. What about now we want to compute the ride duration between a start and an end event. So what this means is actually that we have to relate the start and the end event, right? And in SQL, what is the obvious way for this? You do a join, right? So what we are doing here is we are performing a windowed join. So because the problem is, what if some rides take forever? Maybe some event got dropped, or we don't know. So we want to window the result. We only want to include taxi rides that ended within 2 hours, just to limit the state size a little bit. So as you can see, we are having 2 subqueries. One subquery gives us, let's take this one. We have 2 subqueries. One subquery gives us the start events. The other subquery gives us the end events. We relate them on the taxi ride ID. Then we give it some time constraints about the road times of both events. And then we are computing the duration in minutes here. This is how it looks like. This is how it looks like in Flink. Would look like this. As you can see, we are joining 2 data streams. Let's do something else. Maybe, what else do we have? Let's do this one. So here we are performing multiple things at the same time. So we are computing. First, we are performing a window join, as in our previous example, and then we are calculating just we are calculating the write duration, and then we are calculating the average of all write durations. So whereas this query produced an append-only stream, this query will also produce insertions and deletions because the average is changing as more durations come in. And as a last example, of course, we cannot only print those results on the command line. No, we can also create a long-running Flink job. So as I said, there is Elasticsearch index, or Elasticsearch is running in the background, and the sync is already configured. So what we can do now, just as a simple sync example, we are performing a count, a running count again, grouped by the area ID, and we are just inserting the results of this query into the area count sync. Before I will do this, we can also look into Elasticsearch. Yeah, as you can see, let's make it a little bit bigger. Yeah, no such index found, so the index has not yet been created, but we will change that now by inserting some things. So this is a detached query, so we can now exit the SQL client if we want to. This is now shipped over to Flink. Flink is now taking the responsibility of keeping the job running, like if you have defined a restart strategy in your YAML file. And let's look into Elasticsearch. And as you can see, there is a total count of this, and we can also update, and you can see, yeah, this number is changing, so our Flink job is running. So what can we do now? Yeah, let's use, for example, Kibana, connect it to Elasticsearch, and our real-time dashboard is completed, basically. So I just showed you some of the queries. If you're interested in more queries, just visit the SQL training repository. Just to summarize everything a little bit, yeah, unification of batch and streaming is important because it's quite useful. You can have very nice streaming and batch use cases with it. It already runs in production at several companies, and the community is also heavily working on improving and making it even more easier than it is today. And if you have some suggestions or things that you think are more important that are not on our roadmap so far, get involved, discuss, and yeah, maybe also contribute to the development in this section. Yeah, thank you very much.
Thank you, Timo. I think we have 5 minutes for questions.
Hi, I have a question. Do you have some kind of benchmarks or estimations of the Flink SQL compared to HiveQL or SparkQL?
Not yet, to be honest. Maybe somebody else could do these benchmarks, but no, I don't know. But as far as I know, I mean, compared to Hadoop, the Flink batch part is already very efficient. So I think we should actually be faster than Hive, but I'm not sure about this. So yeah, maybe you should run your own benchmarks on your use cases. Yeah.
Hi. Since we're speaking about Hadoop, do you have the connector for batch processing with Parquet file and ORC file?
So yes, we have those connectors, but in the dataset API. So what we are working on right now is wrapping all the available connectors in Flink in like a table source with a nice schema and everything. So right now what you have to do is you can, for example, use regular dataset connector and convert it into a table, and then you can run your SQL on top of these queries. But also defining sources and things is also documented, so it's easy to extend the existing capabilities here.
Thank you, great talk. If I want to export the materialized view creating state into a database, like you shown in the schema there, do I need to have my own sink to implement the upsert in different database? Or are you going to provide some, like FL Connect, a list of sink operator for writing in database?
So the interesting thing is, like we already have like a JDBC connector, but the same problem as before, it's not well connected to the table API yet, and also it does not support things like upserts and deletions. So you can only insert things into the database. So since the databases are still very popular out there, we will definitely offer some database connector in the near future. Yeah, but I don't know when.
So right now, if I have to write a Flink SQL job, it's either like a Flink SQL job or I go full down the data stream route. Is there anything in the future that's coming where I have one Flink job and I can perform in data stream in one operator, and going further in operators, I can use SQL? Like, can SQL operate on inputs that are coming from other Flink operators, yes, and not directly from the stream? This
is exactly why we are calling it SQL and Table API. So the Table API can also take SQL queries, and it is an API, so you can convert any data stream job that you had before into a table. Do some, for example, just in a simple example, you want to use a quarter function. You don't want to implement some library to extract a quarter out of a timestamp. So you could, in theory, convert your data stream to a table program, perform some ETL, whatever, and then you can convert it back into a data stream and continue with more complex operations like process function or so on. So that's possible.
Okay, thank you, Timo. If you have any more questions, feel free to ask Timo after the talk. We will now have a 1-hour lunch break, a play. Enjoy and look forward to the rest of the conference. Thank you.
Thank you.